Hello, this is going to be a short demonstration video on how to use the Audio Network Analyzer program to measure the frequency response of a simple RC network. The one I'm going to use as an example is this network here, 15K resistor driving a 100 nanofarad capacitor in a low-pass filter configuration. Now, to measure the frequency response of this circuit, we would ideally like to drive the circuit with a 0 ohm output impedance source and measure the voltage across the capacitor with an infinite impedance voltmeter, something like this. In simulation, a 0 ohm output impedance and an infinite input impedance voltmeter is quite simple to use. However, in real life, we're going to be using the VAM. And the VAM output impedance actually looks more like this. A voltage source in series with a 100 ohm and a 22 microfarad capacitor. And the VAM input circuit looks like this. As you see, it's quite complex and certainly doesn't have an infinite impedance down to ground. So just putting our RC circuit, test circuit here, in between the VAM output and the VAM input, we're not going to be measuring just the performance of our test circuit. We're going to be measuring quite a complicated circuit containing the output impedance of the VAM and all of the filter of the VAM input as well, which is not what we're trying to measure. The solution is add buffers. Put a little op-amp follower there and an op-amp follower here. And choosing op-amps, the input impedance, looking into the non-inverting input, is so large it might as well be infinite. And the output impedance coming out of an op-amp voltage follower like this is so low, certainly much lower than 1K, that to all intensive purposes it behaves like it has a 0 ohm output impedance, and now we can determine the performance of our circuit. Just one slight catch. If we simulate the performance of this circuit with two buffers and no test circuit at all, just a wire joining the two op-amps together, then you notice that the frequency response that we measure is not completely flat over the range of audio frequencies from 1 Hz up to 10 kilohertz that we're interested in. It starts to dip a little at the low end, and the phase also is not a constant 180 degrees. It's 180 degrees rather than naught, because this filter circuit here, the VAM input, actually inverts the signal. But it's not a constant 180 degrees. What do we do about that? Well, the solution is fairly simple. It's called calibration. We first take a reading with a wire in place of our test circuit, and we remember what all the readings are for all the frequencies that we measure. Then we put our test circuit in, and we take another reading. The difference between those two readings must be due to the test circuit only. So all we do is take this reading and subtract that reading, and we'll get an accurate frequency response of our test circuit. Right, now to see how to do it in practice. Since we need two op-amps, easiest thing to do is to use a dual op-amp package such as the TL072. This is the pinout diagram of a TL072. This is pin 1 here, then it goes pin 2, 3, 4, 5, 6, 7 and 8 in the usual way. We would want to connect VCC to a suitable power supply, possibly something like 12 volts from the lab power supplies, and connect VEE to a suitable negative power supply, perhaps somewhere around about minus 12 volts, again from the lab power supply. Now, since we want two voltage followers, in both cases the output of the op-amps is connected directly to the inverting input. So we'd have a wire like that and connect a wire like this up here. Then, if this is going to be our buffer on the input stage, we would take this signal and connect it to the output from the VAM. And the signal here would go to our test network. Then our test network here would connect into the input of our second buffer, the output of which would go and drive the input to the VAM. And in this way, our output from the VAM gets buffered, goes through our test network between this point and this point. That signal then is further buffered, and the output from the second buffer goes to the input stages on our VAM. Right, that's the design. You do have to remember, of course, that the output from the VAM will come as a wire with a screen, and it's important to connect the screen to earth of this circuit, the same earth that you use for the network itself if you need one. Okay, let's build it. And here's one that I built earlier. Here is the TL072. You'll notice that the pin 8 on it is connected via this red wire up to here, which is the 12 volt power supply. Pin 4 goes via this blue wire up to here, the minus 12 volt power supply. And I have a ground connection. The 0 volts from my power supply is connecting to this rail on the breadboard, and across this long green wire here to this rail on the breadboard. I've color-coded the wires because that makes it easier to see what's going on and debug. You may not be able to see them, but I've put some tiny little wire links in between pins 7 and pin 6 and pins 1 and pin 2. That's the feedback from the output to the inverting input of the op-amps. Then, the output from this stage of the op-amp, I'm going to use this as my sort of buffer from the VAM output, drives this white wire up to here. The input to the second stage comes from this white wire from up here. So our test circuit we should put between here and here. And to do calibrations, that means just putting a wire between there and there. And I can use this pink wire to put that connection in. Between there and there. Boom, boom. Done. All I need to do now is connect up the output from the VAM's output to the input side of this circuit. So that would involve connecting maybe a pair of crocodile clips up like this. And this is a pair of crocodile clips that I've put on the end of a BNC lead. And the other end of the BNC lead has got a 3.5mm connector on it like that, and I can just plug that directly into the VAM. Make sure that those two crocodile clips don't touch, otherwise we're in trouble. Possibly a bit of blue tack in there just to keep them apart would be a good idea. There, that's better. On the output side, I've actually found a rather more friendly set of wires. I can just connect the shield, the black one, to the ground of my circuit, and the signal itself to the output there. And again, just to stop them touching, bit of blue tack, keep them apart. Fine. Plug the other end of this cable into the VAM's input port on its sound card section, and that's it, we're ready to go. This is what we need for the calibration input, and after we've done the calibration, we would just remove the wire, build the network that we wanted to measure. In the case of the network of a 15K resistor and a 100 nanofarad capacitor, that just means adding in a 15K resistor and a 100 nanofarad capacitor, like so, to build up the circuit that we're trying to measure. And then we would take our real reading. Let's see what happens when we try that. First though, just a quick reminder of where the other end of those leads from our buffer circuits should go. The one that feeds into the first buffer chip should be into there, the VAM sound card out, and the one that comes from the second buffer after the test circuit should go there into our sound card input. We then connect the VAM to the PC in the usual way. The PC will send out some test signals out of the sound card output, through the buffers, through the test circuit, back into the input, back out of the USB port and to the computer to analyze. It's important that you do get these switches set so that the VAM is put into its network analyzer mode, which if you notice means off, off, on this set of switch blocks, and on, off on this set of switch blocks by the out. That done, we're all set up and ready to start running the software.